Hello, everyone. I see the attendees are getting into Zoom. We are already at 25 people, so maybe we can start with today's webinar, New Athena's webinar, the first in this, let's say, new 2024-2025 season. It is a pleasure for me to have here Katja, Professor Katja Poppenhaeger. She's actually professor at the University of Potsdam in the Leibniz Institute and leader of the Stellar Physics and Exoplanet Research section. She's well known for her studies on exoplanet, atmosphere, and in particular, the environment created by their host stars. She got her PhD in Hamburg in 2011, then went for several fellowships, then in the US, for example, at Harvard for a couple of years, and then with the second postdoctoral prize fellowship. And then afterwards, she actually started as a lecturer at Queen's University in Belfast in the UK, till moving to the University of Potsdam, where she's professor now. She has also been in several scientific committees at ESA, like the Astronomy Working Group, for example, and others. She's part of Rosita working group of New Athena since a long time. Athena and now New Athena since a long time for exoplanet and solar system, especially for expertise in her X-ray expertise. So it's a pleasure to have you today. The title of our talk is Mysteries of Exoplanets and Loma Stars and How to Shed New X-ray Light on Them. So I leave the floor to Katja, and I will let you know when you have 5 minutes.
Perfect. Thank you so
Thanks.
much, Nanda.
Go ahead.
Yeah, it's a pleasure for me to be here. Hello, everybody. So let's see. I'm going to share my slides. We checked that this worked beforehand, and I'm going to go to full screen. So as soon as I'm in full screen, I won't see any of you anymore, I think, here in my setup. So if there's any questions in between that are super urgent, just, talk to me because I won't see your comments. So let's see, I have to make this smaller, and now I see actually my own screen. Yes, so I'm very happy to talk to you about a bunch of things that I personally find very, very interesting. And my research field, as Nanda already said, is typically exoplanets and Loma stars. And depending on what your background in the audience is, maybe you don't deal with Loma stars and specifically with exoplanets so much in the X-ray regime. So whenever I'm at let's say at an XMM Newton conference, there's a huge group of people working on much, much more massive objects than I am working on. So I thought today I'm going to give you a bit of an introduction, what we can actually learn about LOMAS objects like Loma stars and also exoplanets from the X-ray regime, and show you a few things that I'm particularly excited about for New Athena, for the next generation of X-ray observations. Okay, so exoplanets and why does my slide not advance? It does advance. There we go. So why do we talk so much actually in the exoplanet context about Loma stars? I want to show you here the exoplanet zoo. This is a depiction of the exoplanets that we have detected so far. What you see on the x-axis is the semi-major axis of the orbit of the exoplanet. On the y-axis, you see the estimated planetary mass. Yeah, and there are actually a bunch of groups here in there. I hope you can see my cursor. So we have here a giant blob of relatively low mass exoplanets that are much closer in than our own Earth. So maybe I want to put stuff in here, yeah? Earth, Venus, Jupiter, Saturn. We basically already see that all of this stuff that we have detected so far typically is much closer in distance to the host star than the same mass objects we know of in the solar system. Yeah, so we have here, for example, this other blob up here, the hot Jupiter. So these are Jupiter-sized and Jupiter mass objects that have orbital periods of something like 3, 4, 5 days. Yeah, so very different radiation environment that these exoplanets have. And the reason why this diagram looks this way is not because here in this empty triangle there are no exoplanets. We very much think that there are exoplanets there, but our current detection methods just don't have enough sensitivity to actually find objects, let's say an Earth-sized thing in an Earth-sized orbit. We can't do that yet. Now, what's interesting in this diagram is if you do a little bit of color coding for what the host stars are doing. So here I have color coded the hot stars in there. So when I talk about hot and cool stars, I'm basically talking about a threshold temperature of roughly 6,200 Kelvin. So this is basically where you, on the cool side, have stars that have an outer convective envelope and an inner radiative zone, and the hotter stars have their outer radiative zone. So this is this divide I'm talking about here. And that's not that many hot stars that we have as host stars. This is mainly also because of our detection methods that work better for lower mass stars. And here you have a bunch of evolved stars in the sample. And that means that the whole rest in this plot here, all the little black dots without any special color to them, are actually cool main sequence host stars. And that means whenever we talk about exoplanets, the vast majority of exoplanets that we know of and that we can knowledgeably talk about are things that orbit a cool main sequence star. Yeah, so that's what typically drives the environment around the exoplanets that we know, what sets their radiation environment, also their particle environment when you talk about stellar winds. And this is why I mainly work on the low mass stars, because they are, in terms of numbers, the most important ones for the exoplanets. Now, I want to talk about a bunch of different parts in such a star-planet system actually here. So I like to show this, this artist impression conglomerate that I've here put together. It seems very extreme in this picture that you have here something like the sun, and then you have here your exoplanet, but actually it's not even that extreme. We do know of hot Jupiters that orbit their host stars within something like 2 or 3 stellar radii. I mean, here I put it even a little bit closer together, but let's say if your hot Jupiter is somewhere out here, that's actually real distances that we sometimes observe in these systems. So we have very extreme systems where we don't have analogs of that in our own solar system. So in terms of what we can talk about in the high energy regime, there's a bunch of different things. We can talk about the site of the host star, where for low mass stars, we have stellar corona, we have flares, we have coronal mass ejections, and so on. And I want to talk just a little bit about that, because there's a vast number of research questions just related to low mass stars that one could talk about. And if I try to do that, we would be here for hours, okay? So I'm just going to very, very briefly graze the surface of that. On the exoplanet side, we can talk about the exoplanetary evaporation, so the mass loss of the atmosphere. You can also talk a bit about atmosphere chemistry and physics that is strongly influeed by the environment that the host star creates. And I'm going to be talking about something that is very dear to my heart because it's tricky, and I really like that, star-planet interactions, specifically the flavor of star-planet interactions where the planet influences the host star, which is a great puzzle that's a lot of fun to investigate. So we go through this a little bit. We start just, as I said, grazing the surface of the low mass star side. And I'm just going to give a very brief overview how these cool stars make their X-rays. In case you work on low stars, you know all of this, but in case you work on other objects, I just want to have you a little bit of background how these things actually make their X-rays. So for the cool stars, like our own sun, we have a very tight connection between the stellar rotation and the magnetism. So what we typically have in these cool stars is that we have a differential rotation, differential meaning that your rotation period is not the same at the equator and the poles of the star, but also if you go inside radially, you have different layers of the star rotating at different velocities. What we get there is basically we have a dynamo process that creates a time variable magnetic field through this differential rotation. And what we see then there over really long time periods, let's say millions, hundreds of millions of years, is that we see sort of a self-regulating process that is called magnetic braking. So the magnetic activity of these stars causes a whole bunch of phenomena. You see star spots, you see surface magnetism, which causes an ionized wind to be shed from the star. And this wind carries away angular momentum. And then what we get there is basically that your star rotates slower and slower over time, which means that the so-called fuel for everything magnetic that is happening on the star reduces also over time, right? In principle, this is a wonderful process that we should understand very well, but once you start looking into the details, it can get very messy. In the X-ray regime, This means then actually that we also see a tight correlation between the X-ray emission of stars and their age. Here is, so to say, a multi-wavelength look at our own sun, where we see the same phenomena manifesting differently in different layers of the solar atmosphere and also in wavelengths. So you see all these beautiful sunspots here in a white light image. And as you now go upwards to the solar atmosphere, here in the chromosphere, you see these emission regions that coincide here with the star spots. So this is typically where you see your calcium H and K emission coming from. And if you go even farther upwards, you reach the stellar corona, which is heated by the same magnetic fields and probably also acoustic waves, where you see here these magnetic field loops filled with very hot plasma. For the case of the sun, this is typically 1,000,000 degrees, can go up quite a bit higher than that. And we see there large time variability. You can see flares happening, we can see magnetic activity cycles happening. These are all active research areas for LOMA stars to understand how this works, because of course in the sun we see it in detail. For stars, we see them typically as point sources, but we have different masses, we can investigate different ages, we can investigate different activity levels. It's great, right? So there's lots of cool things we can do with that. And here I wanted to just put this in typically how our low activity stars can look like versus our high activity ones. If you're an excellent Newton user, you know this very well. You can have these things here, your X-ray bright sources, where you can get your wonderful RGS spectra, and then you have the things where you basically are sitting there with CCD spectroscopy that you will be dealing with. Right. So this is the whole stellar angle, where there's a huge community of people who investigate all the wonderful processes of stars. I also do some of that work, but today I want to focus a bit more on what the exoplanets actually bring into this whole picture. Because the stars are not just mere background candles, we can also look at really interesting physical connections between the stars and the exoplanets. So if we have these exoplanets embedded in the really intense radiation environment of a nearby host star, we have interesting evaporative processes happening, especially for hot Jupiters, hot Neptunes, all those types of hot planets that aren't really something that we see happening right now in our own solar system. So there's some differences. When you look at exoplanet atmospheres in the longer run, let's say about giga years and so on, Gene's escape is something that you will see a lot of the time, but it's a very inefficient type of escape. So basically, you really have just your atmosphere, you have your velocity distribution of the particles in the atmosphere, and if actually you have your velocity vector basically pointing outside of the gravitational well of the planet, and the velocity is high enough to exceed the escape velocity, you get your particles that just escape. But that's really very inefficient. That doesn't cause any observable mass change of an exoplanet on timescales that we want to study. For the strongly irradiated exoplanets, the situation is actually quite different, and then we can easily enter the so-called hydrodynamic escape regime. So what's basically happening there is that especially your high energy photons heat an upper layer of the atmosphere, and this layer then expands. And what happens then is basically that it can push everything that sits above it out of the gravitational well of the exoplanet. And you get a very efficient escape that can really change the envelope mass that your exoplanet may have over timescales of, let's say, a few 100 million years. So that's an interesting thing. It was something that was expected to be observed, and that we actually as a community have observed over the past almost 20 years now. So before I go into individual exoplanet observations, there is also evidence in the whole population of exoplanets that something like this must be happening. So what you're seeing here is another population diagram, right? If you remember from early on, so this is the hot Jupiters, here are the small planets, and there's this sort of bite-sized chunk that is kind of taken out of the population. This is what's called the radius desert. But what I want to talk about is something that is not easy to see in this picture, but you will see it better in the next, is something here that is called the radius gap or the radius valley from Jim Fulton's paper. And what this is supposed to be is a sort of a gap in the exoplanet population that divides the things that are sort of Neptunic in nature, so a rocky core and a hydrogen helium envelope, and the ones that are more Earth-like or super Earth-like. So we're going to zoom in a little bit. So what you're seeing here, yeah, we're relatively close to the whole star orbital periods between 2 and 80 days. And we're now on the y-axis completely with the small planets, so 1 to 3 Earth radii. And there you can actually see relatively clearly that there is actually a gap in these populations. And the idea is where that comes from is really that you have your sort of mini Neptune sitting up here, and in a certain period of their life, in the relative youth of the exoplanet, it loses this hydrogen-helium envelope through evaporative processes, and then ends up sitting here as a bare rocky core. And depending on where this actually happens, depending on what the distance to the host star is and where the habitable zone sits, this can also be very interesting for a secondary outgas atmosphere. Maybe not over here where things are super close to the host star, but you know, if you go farther here, it can be very interesting. So we want to understand how this happens, right? How over what time scales can you lose which amount of atmospheres? How does this actually work? What are the processes that are relevant? There's a whole bunch of interesting studies about this. One angle that I think is very interesting because it really ties the star into this is to consider how the stellar X-ray luminosity evolves over time. What you see here is data from the Udall group. You see here stellar ages, and this is all masses of star masses roughly sun-like. You see here X-ray luminosities, and you see as the star ages that basically this population spreads out quite a bit. There are stars that remain quickly rotating for quite a while and maintain their high activity, and then, this is sort of the blue track here, then they fall down. Or there's others where the rotation becomes lower much earlier in the life of the star, and then you have a much lower X-ray luminosity history of the star, so to say. And this can have different effects on different exoplanets that you see here. This is something that one of my PhD students, former PhD students, Laura Katja, investigated over the past few years. We have built the planetary photoevaporation simulator, where basically you can pick your host star activity evolution, pick your evaporation model that you think is most appropriate for that situation, and then have a look at how the exoplanet actually loses its atmosphere, over which timescales we are talking here, whether there are certain stellar activity evolution tracks that will fully evaporate your gaseous envelope or which will not fully evaporate your gaseous envelope. There's a whole bunch of things you can do with that. Laura also ran many simulations, and what we're seeing here is, again, this gap here. So this is a synthetic exoplanet population, and depending on whether you force all stars to go through a low activity evolution or the medium or the high activity track, the position of this gap and the relative population densities of the mini Neptunes versus the Earth-like exoplanets changes. And of course, the difficult part is that we typically don't know what is the history that the star went through. Although in some interesting systems, there's really great work by Daria Kubishkina with multi-planet systems, you might actually be able to sort of trace back what the activity evolution must have been in the most likely way to have the surviving planets look the way they actually do. So there's lots of interesting stuff to do here. I want to go a little bit now into not the population level. So because everything what I've shown you here is basically you do stuff and then you wait a giga year and then you see how your population reacts, right? But we also want to, of course, study ongoing evaporation presently to see what are the instantaneous evaporation rates, what can we actually infer from that about the stability of exoplanet atmospheres, and about the mass loss rates actually to feed our simulations with the correct estimates here. So, in principle, so this is something many of you will certainly know, the way we typically observe exoplanet atmospheres is that we go for a transiting system, yeah? So you see this here in this standard cartoon, yeah? This is your star, you push your planet in front of it, we are as observers in the same plane, basically, and so we see a reduction of the brightness of the star just because of the geomagnetic blockage that the exoplanet produces. And depending on at which wavelength you observe this, your atmosphere of your exoplanet can either be translucent or opaque. This depends also on the composition of the atmosphere. So if you observe at a wavelength where the atmosphere is translucent, you basically see a shallower transit. And if you go to a wavelength where most of the atmosphere is opaque, you see a much deeper transit, and then can not only estimate the extent of the atmosphere, but also what is actually in that atmosphere. Excuse me. I don't want to go too deep into this, but there was an era, I would say over the past 10 years, where the exoplanet community has tried to observe atmospheres, mainly in optical and near-infrared wavelength, and figured out that sometimes these atmospheres have high altitude clouds or hazes, which sort of messes all of this up, and you basically see flat transmission spectra. I don't want to go into this too deeply, but something that I really like about this is that you can also go to X-rays and UV and have a chance of learning something very powerful, especially in those cases where the infrared doesn't help you much. So how does this work? What you're seeing here is the transmissivity of our own Earth's atmosphere, right? This is the standard picture, so visible photons reach the surface. And then here in the infrared, you have this reduced transmissivity of our atmosphere, which is mainly water vapor. And then here you see also at the shorter wavelength, so basically your UV and X-ray photons are absorbed quite high up in the atmosphere. So for the Earth, the X-ray radius is roughly 100 kilometers more than the optical radius for the type of atmosphere that we have. So what does this mean, right? So let's say in your standard white light optical, this is your transit depth. Typically, if you have then an atmosphere where there's something in it that scatters photons in the infrared, you can see a slightly deeper transit there. But also, you should expect to see a much deeper transit typically in UV and X-rays for most atmosphere compositions that we can think of, because usually your cross sections with the UV and X-ray photons tend to be quite large there. So has this been done? Does this actually work? So this is one of my older works here that got me very excited about this idea. So there I collected several transits of hot Jupiter. This is one of the hot Jupiters with the biggest transit depth and the one that's relatively close located to our own solar system. It's called HD 199733b. And after co-adding several X-ray transits collected with X and Newton and with Chandra, I was actually able to find evidence that this X-ray transit is actually a good bit deeper than the optical data. So what you're seeing here, I always have to say a little bit about that. The optical data is your standard transit depth. The black data points is what you get out of that. And then really this purple line, what you would expect to see is a so-called limb brightened transit, right? Because you have here this sort of limb brightening of a typical star, but this is not something that I was fitting at the time. So you can just fit this also with basically a flat bottom transit, and it makes barely a difference in the fit quality. But in principle, we would expect sort of a W-shaped transit if you observe in UV and X-rays because of the stellar limb brightening. Okay, so far, this is still the only exoplanet where an X-ray transit measurement has actually worked. And the reason for that is that on one hand, there's not that many very nearby hot Jupiters. So you're flux limited with the X-ray flux. Yeah, this system here is roughly 20 parsecs away, and it's very lucky that it's such an inflated hot Jupiter that produces a relatively deep transit of 2.5% in the white light optical. But there aren't that many others around. You need a very X-ray bright host star so that you can beat down your counting noise, right? If you do that with current X-ray telescopes. And then you still need to find something that makes a deep transit. So this is something where we're currently very much flux limited, and where I think in the future we can do much, much better and have many more exoplanets where we can do this with and actually study what is the extra transit depth we see in X-rays, how does that relate to different atmosphere types and so on. Apart from the X-rays, what people have also done to study these evaporating atmospheres, and maybe I should say this actually explicitly. So a deeper transit in X-rays and UV doesn't necessarily tell you that the atmosphere is evaporating. At some point, when the X-ray transit or UV transit gets deep enough that you know, okay, this thing I'm seeing here is Rochelot filling, then you know it must be losing mass. But that is not always the case. So you need to really have a strong case here. And this is one of those extremely strong cases. This is wonderful data. This is a hot Neptune. And what you're seeing here is a lot of stuff going on in this picture. But what you're basically seeing here, the dashed black line here, this little thing, is what the transit looks like in white light optical. What you see here in red and blue is actually HST observations of the red and the blue wing of the Lyman alpha, the hydrogen Lyman alpha line. And if you see this, basically, if you take the maximum depth that happens here, I mean, almost 40% of the stellar disk is being occulted by something that absorbs in hydrogen Lyman alpha. And also you have this curious offset after the actual transit is already over, which led to this really interesting interpretation that we're basically seeing a huge comet-like tail of evaporating atmosphere that is being blown off this exoplanet. You get this huge signature. Really interesting one. This, by the way, is a host star where you currently cannot do the same experiment in X-rays because a host star is quite faint. And this, you don't get enough photons in XMM to actually look at what is happening at X-ray wavelength, unfortunately. If you follow exoplanet evaporation stuff a little bit, you will have noticed that in the past few years, people publish a lot about extended or evaporating atmospheres in helium. So helium has a bunch of absorption lines in the infrared, where basically what you're seeing here is a super deep transit of a hot Jupiter in these helium lines. Now you might be wondering, why are we talking about infrared stuff? I'm going to tell you in just one moment. I just want to show you something really cool about this, because what people did here, so this is Carolyn Morley's team, is basically that they saw a very deep transit of the atmosphere, but they saw already this transit beginning and lasting much longer than the white light transit. So it's not just cometary tail being blown off, but what they actually modeled is that we have an exoplanet here. We are basically watching from the side, so from within the plane of the image, where we have some evaporating material from the planet falling onto the star and other material from the planet being sort of blown away and forming kind of a ring here. This is interesting because there were predictions for something like this happening by Ignazio Planetary and also by Antoine Strugerek in his simulation. So this is really exciting for me to see. And now the connection to X-rays, actually. So we go a little bit into what is happening here. So these helium observations are really, really powerful. People do these now sometimes with mid-sized ground-based observatories. This is fantastic how clean the signal is in comparison. However, these specific lines, these absorption lines of helium, are the so-called metastable lines, which means the ground state is not involved. What's basically happening is if you have helium in the ground state in your exoplanet atmosphere, you don't see anything in those infrared lights. So basically the infrared light just goes through. But if you make the helium go into this metastable state, which basically happens through irradiation with high energy photons, then it's in the correct state to actually scatter those infrared photons. It means if you have enough high energy irradiation of a specific exoplanet atmosphere that you are observing, you will see a big helium absorption signature and you can trace the evaporating atmosphere that way. If you don't have enough high energy irradiation, you might still have some kind of outflow, but you're not going to see it at those wavelengths. And this is something that makes the interpretation of these data sets quite challenging. But I think for the X-ray regime, this is actually great news because there's so many interconnections between optical and near-infrared exoplanet observations and a real strong need to characterize the stellar high-energy spectrum that we really need this component to understand what's going on in our exoplanet systems. So if we want to estimate the present-day X-ray radiation of planets, there's a bunch of stuff we can already do now. For example, we can work with data from the Rosetta X-ray survey, where we've recently worked with this. This is also one of my former PhD students, Grace Foster. So what you're seeing here is the location of exoplanets in the sky. These are the gray dots, and in the German part of the Rosetta data, you can see all those pink dots where there are new X-ray detections of exoplanet host stars that we can now characterize. We can say more about what's going on there, what you're seeing here. And I'm just going to show you quickly two plots here. These are the irradiation, the X-ray irradiation levels of exoplanets that come from that, and some estimates for the mass loss rate. And basically the takeaway is here, there are actually a whole bunch of interesting exoplanets which we should observe further to figure out how their mass loss actually works, because we can characterize their X-ray irradiation. Now, I want to highlight a recent paper that I read on the arXiv. This comes out of the group of George King. This is really cool stuff because they actually simulate the potential for observing X-ray transits with new Athena specifically. And this is a great paper. I encourage everybody to read it. Sille, King, and Corrales. What you see here is simulated data for an X-ray transit depth of 2.5%. So this is basically a relatively shallow X-ray transit that you would be able to actually observe and characterize. You see they also use here this type of W-shaped model, as we should expect. And they show a lot of interesting things here, basically, which exoplanets that we already know of would make very good targets to observe with new Athena. So they show this here as a function of logarithmic transit depth of the exoplanets and the X-ray flux. And here you see basically again how these objects scatter in this plane that you've seen now a few times with this exoplanet gap. Yeah, so here's again the orbital period, and here's the radius of the exoplanet, and these all tend to be sort of in the Jupiter, Saturn, Neptune-ish size range that actually becomes accessible. And you see it's not going to be just one exoplanet anymore that we can study like this, but it goes up to roughly 15. And this is a really interesting thing, and I think very cool that we have these estimates. Now, I want to shift now a little bit from the exoplanets to the star-planet interaction. The star-planet interactions are something that is really exciting. The fundamental idea is, you all know closed stellar binaries, right? We have a bunch of interactions that closed stellar binaries can have. There's tidal interaction in those. There can also be magnetic interaction. And along those lines, if we basically treat a star and an exoplanet as a closed binary with a very uneven mass ratio, maybe we see some similar effects there, even on a slightly weaker scale. And why is that important? It's important because then the magnetic activity evolution and maybe even the rotational evolution of hot Jupiter host stars is not the same as for single stars without hot Jupiters. We need to take this into account in our expectations for the radiation environment of these exoplanets. So for tides, how does this work? Let's say we have here the star, the orange one, we have here the planet. Typically, a stellar rotation period of a normal star that is of somewhat mature age, let's say like the sun, is rotation period roughly 30 days. Or if it's a bit younger, let's say 20 days. If this is a hot Jupiter, then its orbital period is much shorter than that. It can be 3-4 days, something like that. And that means that the exoplanet is faster on its orbit than the star rotates. And we basically get this tidal torque here, yeah, where the exoplanet is kind of pulling on this lagging tidal bulge here on the host star. And what that means is that over time we have an angular momentum transfer from the orbit of the exoplanet into the spin of the host star. So this is basically the opposite of what's happening in the Earth-Moon system. Yeah. So that means that over time the exoplanet spirals closer into the host star, and the exoplanet host star spins up in the process. Question is, how do we observe this? Oh, wait, I go back to this one here. So the problem is that usually for most single stars, field stars, we don't have a good age estimate. For some reason, we can get astroseismology, it's great, but for most of them, we don't know the age. So if we say, okay, we have an anomalously fast rotating host star here, how do we actually know that's anomalously fast if we don't know the age? Maybe it's just a young system and it's okay that the star is relatively fast rotating. So what we've been doing for quite a few years now is we try to observe these planet-hosting stars when they reside in wide binary systems with another star. If we have another star there as basically a negative control, we can search for these discrepancies in rotation and activity evolution. And here is then the idea, if we have these things here, they are co-eval, they have the same age, the thing with the hot Jupiter might have preserved faster rotation and therefore higher magnetic activity than the other star in the system. And this is some recent work of one of my group members, Nicoleta Illich here. She's been studying this for a few years now. You see here an XMM observation of a wide binary, one of which hosts a close-in exoplanet. And what you see here is the result that Nicoleta Illich has found. So what you're seeing here is basically on the x-axis, we have a measure for the tidal interaction strength between the star and the exoplanet. And here on the left are the ones that are expected to interact strongly. These are the ones that are expected to have only very weak tidal interaction. And here you see a measure for the activity, the X-ray activity discrepancy between the planet host star and the negative control star. You actually see, even though there's quite a bit of scatter, the trend as such is highly significant that we have these stars up here with the close and hot Jupiters being overactive compared to the other stars. And this is a very exciting thing because we now, for the first time, have this sample evidence that really the exoplanets can make a difference to their host stars over the long timescales. By the way, here's HG 189733b, yeah, our good old friend with the X-ray transit. And you see a lot of this stuff is relatively volume limited, and you see your old friends over and over in the stellar regime because there's not that many stars around where we can do this experiment with. I also want to spend just a few minutes to talk about magnetic star-planet interaction, because this is something really exciting, something really cool. The original flavor star-planet interaction by Evgenia Shkolnik looked for these types of things. So the idea was basically that there would be chromospheric hotspots that could be induced by the planet. And that's really highly interesting work. It's really something that would be very cool to have some kind of magnetic reconnection happening here that could heat parts of the stellar atmosphere. And the problem is that this is always really hard to distinguish from the relatively stochastic changes that the stellar magnetism shows anyway. I mean, if you look at the sun and you look at its changes, it's actually not all that smooth. Yeah, you have, of course, the 11-year cycle, but you have many things like flares happening, other small changes in activity happening that we can't predict. And so it's actually really quite hard to tell apart. There's a bunch of things, how one might try this. There are some things we have done in my group, but I want to highlight one approach that I particularly like. And this is this idea here that you could try and search for magnetic star-planet interaction when you have an exoplanet in an eccentric orbit. Yeah? So you have your planet moving around here. And so in principle, whenever the planet is relatively far away, you should expect no magnetic star-planet interaction. And as soon as the planet comes in, that would be the point in time where you would expect magnetic star-planet interaction to be triggered. You could care about this only from a stellar perspective because it's a really cool thing. But the reason why we from the exoplanetary side care about this so much is that in some way, the strength of this type of interaction and whether it happens at all should depend on the planet's magnetosphere. And planetary magnetospheres are super exciting. We think they are important for habitability, but so far we haven't measured any planetary magnetic fields outside the solar system. So this is kind of a holy grail to somehow find information on planetary magnetospheres. One paper that I think this is still actually the only one. I keep looking for things like this, but this is from the Maggio group. It's already a number of years old. But there's something really cool where they did exactly observations like this, X-ray observations of a very eccentric system here, of this eccentric Jupiter with this telephone number. And so to explain the data a little bit, this thing here, this in the big white circle, is actually not the object that we want. That's a background object that's just always there in X-rays. But here, where you have the little green square is basically the location of the exoplanet host star. The orbit of the exoplanet is not resolved in this image. So it's basically all one point source. But when the planet is out of periastron, you don't detect in these two leftmost images here, you don't detect the exoplanet host star. But the two times where that team looked during the periastron passage, they actually found that the host star is detected in X-rays here. So there's a significant brightness increase. And now you can, of course, say, okay, what are the chances, right? You can run some statistics here and say, okay, stars flicker in X-rays all the time. Maybe this is just lucky or unlucky, depending on how you want to call it. And it tends to be quite hard to convince time allocation committees to give people large amounts of observing time to do stuff like this, right? But I think this is a fantastic example of how these experiments can be designed, where you can find out something and really beat the typical stellar activity noise that we just see in cool exoplanet host stars. And I think, yeah, I've been talking a little bit fast because I'm already coming slowly to my conclusions here. So I think the X-ray prospects for star-planet systems in the new Athena era are really bright. There's lots of fantastic things we can do. On the host star side, and I haven't talked about it so much in terms of just the stars, right? There's other people who could give you a wonderful talk about everything low mass stars. But I think in terms of the exoplanet interest, it's quite important to characterize the stellar X-ray spectra also for things that are older, low mass M dwarfs. Yeah, if you think of exoplanet systems like TRAPPIST, also Proxima Centauri, that is nearby enough to give you a lot of X-ray counts. But there's a lot of M dwarfs out there where we know of small exoplanets that become very interesting also for James Webb. And you keep seeing that people try to find an atmosphere with James Webb observations, and it turns out the thing is a bare rock. And I think it would help us a lot if we knew the X-ray environment of these exoplanet atmospheres beforehand. We had some idea whether these atmospheres should be expected to be fully evaporated already. We should also aim to improve the age-activity relationship of stars wherever possible. This is a messy thing. It's not easy, but I think it's going to be very instrumental for understanding exoplanets better. In terms of the planets themselves, I'm super excited about the fact that we are slowly getting within reach of enough X-ray sensitivity that we can measure transit depths, not just for one exoplanet that happens to be really nearby located, but for an actual representative sample of exoplanets. So where we can study how is this different for a Neptune versus a Jupiter? How is this different for different planet masses? How is this different for different regimes of evaporation that we might expect for these planets to exist? And I think this is something really important that we can actually do with new Athena. For the star-planet interactions, I think there we have a vast playing field where we can do really cool things. Currently, the volume that we can use for studying this is relatively small. We're talking in terms of the tidal star-planet interactions, maybe 15, 20 systems, and then we are already limited by X-ray flux in principle. Yeah? So it would be great with a larger sample to quantify these tidal star-planet interactions for different stellar masses, especially for different stellar interior structures, because that tells us also how long exoplanets survive in such an orbit and how quickly they should be spiraling in. It would be also extremely interesting to identify whether this kind of flare triggering by star-planet interactions is actually a ubiquitous phenomenon or not, because right now we have in X-rays one great example that I find is suggestively pointing into a direction, but I would find it hard to call it evidence that we should expect this to happen very often. So to do this with much higher sensitivity is actually a fantastic avenue to figure out how planetary magnetic fields interact with stellar ones. And it gives us also a way to say, hey, we have exoplanets here that must have magnetic fields. Maybe we can even, from the strength of these interactions, do some estimates what the magnetic field strengths of exoplanets might be. And that would be very, very instrumental to inform our view of habitability of exoplanets in the long run. So all in all, I think it's very exciting times ahead. I'm glad to be an exoplanet and stellar astronomer and an X-ray astronomer at the same time. I think there's going to be very cool things to learn. And with that, I'm very happy to take any questions that you might have.
Thank you very much, Katja. It was extremely nice, very clear. Any question? If you higher your hand, I can open your microphone. No? I can maybe start. I have a question, a more general one from somebody which is sort of out of the field, but very interested in it, especially on the prospect for new Athena, of course. So you didn't mention in depth, or maybe you did, but it was fast about X-ray spectroscopy. So what can the advantage that we will have with new Athena about X-ray spectroscopy will bring in your fields exactly?
Yeah, so I haven't mentioned it actually. You're right to notice that. I think for me, the most exciting thing to do with spectroscopy would actually be to get a transmission spectrum of an exoplanet atmosphere at high energies. This would be really great. We could actually learn many things, and currently this is completely out of the capabilities. Yeah, we are struggling. If we just put everything broadband together, we are just struggling to even detect the transit in exoplanets. But actually doing this in an energy resolved way and getting some information about the column densities and the material that we actually have there would be absolutely fantastic. I think with the new Athena redesign, maybe this is something I would want to do the math on again, how many exoplanets we should actually hope to be able to do this for, because of course this will be a thing that's going to be quite photon sensitive in the end. Yeah, we need as many photons as we can for this. But this is something that I would find highly exciting. Yeah.
Okay, thanks. So we have a first question by Oisin Greener. I can open your microphone if you want, so you can just ask the question.
Hi. It's given the X-ray emission extends beyond the optical surface of the star, and also atmospheric X-ray absorption extends beyond the optical surface of the planet. I would imagine that those two effects essentially act in opposition to each other. How do you disentangle those effects when you're looking at the transit depth?
Yeah, that is something that is really exciting and not all that easy, right? Because you are exactly right. If this would be my photospheric surface of the star, then the corona has some sort of scale height where we actually still see the X-ray emission. I think to do this right, it would be really helpful to study the extent of stellar coronae for different activity levels much better. For example, if you do eclipses of a cool star and let's say a white dwarf or something like that, to actually trace this out and form an expectation value of what the typical coronal apparent size would be, that would be really helpful to inform this better, because otherwise, unless, well, you can untangle it a little bit if your exoplanet is not directly transiting on the equator, but a little bit above or below, because then the geometry works out a little bit differently. But I think this is something where we would want a good picture of stellar coronae and their extent as such to make this job a bit easier.
Thanks.
Thanks a lot. More questions? If you raise your hand, or you can write them in the Q&A session too, if you prefer. No? Okay, so I have another question about the, oh yes, we have one. So let me, because I asked one already. We have one from Ulrike Heiter. Let me open your microphone. Give me a second. Yes. If you unmute, it should work. Yes, go ahead.
Yes, hello. Yeah,
Yes,
thanks.
hello.
Very nice and clear talk. I was wondering to study these star-planet interactions in the similar, so based on these high eccentricity orbits. What kind of eccentricities are needed to, or I mean, you would say that such flares are triggered?
Yeah, that's, I mean, from the data side, we just don't know yet, right? But what I would personally
Now I cannot
expect
hear
is,
anything.
oh, you cannot hear me? Let's see, is this better? Can you hear me? No, Nana can hear me. Okay.
I do. I hear
Okay,
you.
then maybe there was just some hiccup. So what I would expect, I mean, we don't actually know is a short answer, but what I would expect is that at the
You cannot
periastron,
hear. Maybe
you
I have
would want the planet to be within something like 2 stellar radii or so, because you want really something for an ideal case to be almost having the planet almost within the outer structures of the corona, and then you would want to be far enough away from that at the upper astron to not have that interaction anymore. But I really struggle to tell you, you want at least 0.4 or you want at least 0.2, because we honestly don't know. Yeah.
Thanks, Katja. More question? No, if not, I have a last one, if nobody, so which is again a very basic one. So most of those systems, at least the one which are close enough for which one can detect all the planetary systems, all the planets around, they usually have several planets, right? Not just one, of which, of course, it's easier to detect the most massive ones, but there might be many, right?
Correct.
Now, when we have, you showed these nice X-ray transients, these few that could be discovered, right? Now, I can imagine that if we have the very high resolution that optical data do have, if you have several transients at the same time, you would see it.
Yes.
What about an X-rays? And can that also be a bias? Because your signal is so subtle that you have two, one on top of the other, it can sort of be difficult to disentangle, or not?
Yeah, so this is something that is from time to time actually seen in the optical data, because yes, you're right, most of these systems tend to be flat, so sometimes we actually have 2 planets transiting at the same time. On the optical side, sometimes we treat them as an interesting curiosity, but it gets very, very messy if you want a transmission spectrum or so to actually disentangle it. So if I could just pick and choose, I would say I would always try to target single transits and not try to mess with it. The good thing is that from the optical data, we know the timing really, really well. So, I mean, whenever we look at something, we see something in the X-rays, at least we can tell with very high accuracy if there's already a second planet moving in or if we are far from that situation. But at the moment, with the level of what we are doing also at optical wavelengths, I would say it is quite messy and we try to avoid accidentally observing that.
Okay, okay. Yeah, makes sense. Thanks. Any other questions from the attendees? No? Okay, so if not, let me thank Katja again, which was a fantastic seminar and actually very interesting,